What's up, guys? Welcome back for another Minecraft tutorial. Today, we're going to be doing an angular momentum physics problem. But before we get into that, I want to give a shout out to our official sponsor, Slater. They provide great free homework help, and they have even better merch. Slater. They were there for me when no one else was, and they'll be there for you too. Alright, guys, now let's get into the problem. So for the problem, we are given a description of a situation, a diagram for that situation, and 5 parts to solve. Let's start by taking a look at the description of the situation. Okay, so a girl with a mass of 60 kilograms runs to the left of a merry-go-round at 5 meters per second and jumps on the rim of the merry-go-round, which is rotating at 4 radians per second. The radius of the merry-go-round, R, is 3 meters, and the merry-go-round's moment of inertia, or rotational inertia, about the pivot point, the merry-go-round's center, O, is 400 kilogram meters squared. And now let's take a look at our diagram of the situation. So the diagram actually has 2 parts. The first part shows the girl in the merry-go-round before she hops onto it, and the second part shows the girl in the merry-go-round after she hops onto it. In that first part of the diagram, we see the girl running towards the left side of the merry-go-round at 5 meters per second, her mass 60 kilograms, and we see the merry-go-round rotating with an angular velocity of 4 radians per second. But this angular velocity is actually going to be negative 4 radians per second because the merry-go-round is rotating clockwise. And as we see in part A, and as the general physics rule tells us, counterclockwise is positive, clockwise is negative. So that will be negative 4 radians per second. And we also see the radius R, which is 3 meters, and the center O, which is the pivot point in this problem. And in the second part, we see the merry-go-round rotating clockwise at an unknown velocity, which we will solve for later in the problem. And we still see that radius R, that center point O, and now the girl is on the outer edge of the merry-go-round. Finally, we've gone over the situation and the diagram, so now we are ready to solve for part A. Part A says, let counterclockwise momentum be positive, as we mentioned earlier, and then it asks, what is the running girl's angular momentum about O, the center of the merry-go-round, in units of kilogram meters squared per second? So to solve for the girl's angular momentum as she runs around the left side of the merry-go-round, we just multiply her rotational inertia by her rotational velocity. And so first we have to solve for her rotational inertia and rotational velocity. And to do that, we'll use her linear velocity, her mass, and the radius of the merry-go-round. So first we solve for rotational inertia, which is just going to be mass times radius squared, since she's essentially a point rotating about a central pivot point, which is O. And we'll plug in our 60 kilograms times 3 meters squared, and we will get 540 kg meters squared. Okay, now we have her rotational inertia. We can solve for her rotational velocity, and to do this we're just going to multiply her linear velocity by negative 2 pi radians, which is 1 full rotation in the clockwise direction, that's why it's negative, all over the circumference, which will be 2 pi radius meters. That'll cancel out the meters, leave us with radians per second. And this all will simplify to velocity times negative radians all over r, which is the radius. So the girl's rotational velocity is going to be 5 meters per second times negative radians all over the radius, 3 meters, and we're going to get negative 5 over 3 radians per second. Now we can plug and these two values to find her angular momentum. So 540 kg meters squared times negative 5 over 3 radians per second. And that's going to be 540 times negative 5 over 3, negative 900 kg meters squared per second. And since mass has 2 sig figs, we'll go with 2 sig figs. So her angular momentum will be negative 9.0 x 10 squared kg meters squared per second. Part A is done. On to part B. What is the merry-go-round's angular momentum about O before the girl jumps on it? Part B is going to be much, much easier than part A because we just use that same equation for angular momentum, rotational inertia times rotational velocity, except they've basically already given us the rotational inertia and that rotational velocity. The only distinction we need to make is that this is a negative 4 radians per second because, like I've said before, clockwise. So the angular momentum of the merry-go-round is going to equal that 400 kilogram meters squared times negative 4 radians per second. So angular momentum 400 times negative 4, I'm obviously going to be negative 1600 kg meters squared per second, and we'll stick with the 2 sig figs. We'll pretend this is 0.0. So LM equals negative 1.6 x 10 cubed kg meters squared per second. Time for part C. What is the total angular momentum of the system consisting of the girl and the merry-go-round? If you thought part B was easy, you're going to love part C, because in part C, we don't even have to multiply. All we need to do to get the total angular momentum of the system with the girl and the merry-go-round is add the merry-go-round's angular momentum and the girl's angular momentum. And we'll get that total angular momentum, which will be a constant value throughout this problem because of the law of conservation of angular momentum. So it doesn't matter if we take the angular momentums of the merry-go-round and the girl before she hops onto the merry-go-round or after. This LF, this total angular momentum, it'll be the same no matter what. So let's take the before values to find LF. So the total angular momentum is going to equal that negative 1600 kilogram meters squared per second for the merry-go-round plus, well, actually minus, since it's negative, 900 kilogram meters squared per second for the girl, and we will get negative 2500 kg meters squared per second. And we'll go back to our 2 sig figs, negative 2.5 x 10 to the 3 kg meters squared per second. All right, part D. Compute the moment of inertia of the whole system with the girl on the merry-go-round in kilogram meters squared. So to solve for the moment of inertia of the whole system, we just add the girl's rotational inertia and the merry-go-round's rotational inertia, which are going to be constants in this problem because for the girl, mass does not change, radius does not change. For the merry-go-round, its shape and radius both stay the same. So we just add the 540 kilogram meters squared that we calculated for the girl in part A and the 400 kgm squared for for the merry-go-round, which we were given in the description of the situation. So this is going to be obviously 940 kgm squared. And with our two sig figs, 9.4 x 10 squared kg meters squared. We made it to the last part, part E, and it asks us to calculate that final rotational velocity in radians per second of the merry-go-round with the girl on its outer rim. To find that final rotational velocity, all we're going to do is we're going to use the angular momentum equals rotational velocity times rotational inertia equation and solve for rotational velocity. And what we'll end up with is rotational velocity equals angular momentum all over rotational inertia. So we'll just plug in the values we solved for earlier on in parts C and D, and what we'll get is negative 2,500 kg meters squared per second all over 940 kg meters squared. And what we're going to get is negative 2,550 over 940, negative 125 over 47 radians per second, but we'll simplify that to negative 2.7 with our two sig figs radians per second. So when the girl hops onto the merry-go-round, it'll rotate clockwise at 2.7 radians per second. And we did it, guys. We solved all 5 parts to this problem. If you enjoyed this video, smash that like button. If you have any questions, leave them in the comments below. And don't forget to subscribe. Again, shout out to our sponsor, Slater, for making this video possible. Thank you guys, and see you in the next Minecraft tutorial.